टाइम भी नहीं खावा शुद्ध खावा सर एक्चुअली बाजा के साथ सुनते ऐसे सिलेक्टेड तो बाजा के साथ सुनते हो एक दुख तो दूसरे के खेला है কিন্তু 130 কিন্তু 130 কিন্তু প্রবলেম হচ্ছে অন্য জায়গায় দুই পয়েন্ট বলেছে 130 থেকে 230 মধ্যে না গেলে যা খাবার বেশি হবে বাড়ি নিয়ে চলে যাবে Good afternoon all. Am I audible? Can you hear me?
Good afternoon, sir.
Yes, sir.
Good afternoon, sir.
Good afternoon. Okay, thank
Good
you.
afternoon, sir.
Yeah, thank you. So hope all of you have got good marks in second semester examination. No? Just you have got your result. So is it okay? Are you satisfied with your marks? Are you all satisfied with the marks that you have got?
Yes, sir.
Yes, sir.
Yes, sir.
So is there anyone who is opting for stream change? Because I think you have got the notice regarding stream change.
Yes, sir.
In which stream do you want to go, Vijay?
Sir, actually, I feel the CS, IoT, and IT. There were two preferences we have to give. So first preference was CSC, IoT, and another one IT.
Okay.
I felt that.
Is there any other? So I personally hope that you will all be here so that I could interact with you. But it's an opportunity for you. If you wish to change the stream, then you can go for stream change. But nowadays, if you study in some streams, say for example, you are studying triple E. So after completing your BTech, you can actually do IT job. There is no problem. Or for research also, you can work with interdisciplinary studies. You can go for interdisciplinary studies. So the stream is not a big problem actually. But if your wish is to study, you can obviously change the stream. So apart from Abhishek, is there anyone who is going to change the stream?
No, sir.
Harshit, what do you want to go?
No, sir. No, I say no.
Oh no, okay, okay. So apart from Abhishek, no other is there who wants to change the stream? Okay, so that's very good. Okay, so just I'll summarize whatever I have discussed in the last class. So in the last class, I have started discussing the limit. So how to find out the limit for a function of complex variable, and I have compared it with the limit for function of one variable and function of two variable. two real variables, and I have also told that while we are finding the limit for function of complex variable, we can just compare it with the method that you have used to find out the limit for function of two real variables in first semester. So also I have shared the first class note in the Google Classroom where some problems are there for you to solve. So I hope some of you have some of you have already gone through. So those who have not checked it yet in the Google Classroom, so I'll suggest you to go through once, and if you have any kind of doubts or queries, you could ask me. Obviously, there is no problem. So today I'll be starting the differentiability of a complex valued function. So first I'll discuss what is the differentiability and what are the significances. So similarly here also, like limit and continuity, whenever I have discussed it for function of complex variable, I have discussed or I have compared it with the previous knowledge. That means how to find out the limit or continuity for function of one real variable and function of two real variable. Similarly here also I'll do the same thing so that you can actually incorporate your previous knowledges here and you can correlate the things that we'll be studying here. So just let me share the screen first, then I'll be. Can you see the blank screen?
Yes, sir.
Yes, sir.
Okay. So
Yes,
here
sir.
we'll be studying the differentiability of complex values. So if you change the stream in maths, I think you won't be any having problem because the syllabus is same in maths for all the streams in IEM. Complex function. So before discussing that, I'll discuss the differentiability of function of one variable. So you have found that a derivative of y equals to fx. So at any point x equals to x0, if you find the derivative, so this is denoted as dy dx at x equals to x0 or f dash x0. So this one. So can anyone tell me what is the significance of derivative, or why do we differentiate a function? What is the significance? Anyone? You have already studied in class 11, I guess, I know.
To find the slope or rate of change, we
Yeah.
differentiate.
Slope or rate of change. Okay. So there are different applications of derivative or differentiation. So firstly, if you consider a function of one variable, say y equals to fx, then at any point we can draw the tangent to measure the slope of the tangent. So if this is angle is theta, so tan of theta equals to actually f dash x. So I can measure this by derivative. So what are the significances of derivative? So why do we differentiate a function? So there are lots of applications, but I'll be saying one or two which are very useful. So firstly, if you consider the motion of any particle in one dimension, sorry, in two dimension, that means if I consider the circular motion of a particle, then you know that at any instant the direction of the movement of the particle will be along the tangent at this point. Similarly, if the particle is here, so the direction of movement will be in that direction if a particle traverses along the anti-clockwise direction. Similarly, at this point the direction will be this. So at any point, if I consider the movement of the particle or motion of the particle, so direction of the movement will be identified by virtue of the tangent that we can direct. So at any point, the direction can should be unique. So that's why if derivative exists for a particular function at a given point, so it should be unique. Okay. Then if I consider this curve, say this is a curve, a particle is traversing through that curve. So at any point, we can actually measure the direction, or we can identify the direction of that particle along the tangent. So this is one problem. And another usefulness of finding out the derivative is that, so if you consider a system, so in system there can be one derivative, one independent variable, and there can be more than independent variable if we consider real system. So let's say if we consider the population of India. So this is a dependent variable. So there are lots of factors depending on which the population of India is increasing actually. So if I provide say for example the socio-economical condition, the literacy rate, all these are factors. So if I want to identify what is the population increment with respect to a certain independent variable, let's say with respect to illiteracy, then it is not possible for us to identify this from the gross population. Say for example, in 2020 the population density is 138 crore, 2022 this is 142 crore. So whether the rate of increase is steady or it is actually increasing, we won't be able to measure from the gross amount. So then we need to measure the rate of change of the dependent variable with respect to independent variable. So if we can measure the rate of change, so we can identify with respect to the independent variable what is the change of the dependent variable, so that we can actually analyze the system. So that is actually the application of the derivative. So these are all significance of derivative. So you know, by first principle we can measure the derivative. What is the first principle? All of you have studied this. So for example, if this curve is given y equals to fx, so let's say we want to we are asked to draw the tangent at this given point x0. So we are taking this ordinate, that is f of x0. So the coordinate of this point, since this point is over the curve, so the coordinate of this point will be x0 comma f of x0. Then we are taking a small length, that is del x length. So small length, then the ordinate will be this. So the coordinate of this corresponding point will be x0, because this length is, this difference is del x, so this point will be x0 plus del x. So the coordinate will be x0 plus del x comma f of x0 plus del x. Now we are joining this chord, so this chord will make some angle theta. So this angle will be same, this will be theta. So tan of theta will be this divided by this. So this ordinate, length of this ordinate is f of x0 plus del x, length of this ordinate is f of x0. So the difference will be f of x0 plus del x minus f of x0. And this breadth will be, this base will be, actually this length is x0 plus del x, this is x0 up to this, so this difference will be del x. So here this is the change in dependent variable, because dependent variable is getting changed from f of x0 to f of x0 plus del x, and independent variable is getting changed from x0 to x0 plus del x. So this total change is del x. Okay. So whenever this point will traverse towards this point along this curve, then this chord will be actually converting to the tangent at this given point. So if this point comes closer to this point, so gradually this difference will be tending towards 0. So this limit tending to 0 is actually, if this limit of this quotient exists, then this is denoted as f of x0. So this is the significance of derivative. You have used this first principle to check the existence of derivative of a given function at a particular point. So just I have discussed this so that you could remember it. Now if I move towards the function of two variables, let's say z equals to fxy. So here the number of independent variable are 2. In the previous case, the number of dependent variable is 1, number of independent variable is 1. So we can measure the rate of change of dependent variable with respect to only one independent variable. So there comes the ordinary derivative. Now here the number of dependent variable is 1, but the number of independent variables are 2. So how we could measure the rate of change of z with respect to both the independent variables simultaneously? So it is not possible. So that's why while we are trying to, because if I want to measure the rate of change of these with respect to both the variables simultaneously, then you won't be able to identify whose impact is more on the dependent variable out of these two independent variables. So while we are measuring the rate of change of z with respect to x partially, because we need to keep another variable constant, another independent variable constant. Similarly, we can measure the rate of change of z with respect to the independent variable y by keeping the independent variable x as constant. Okay. So what are the significances of this partial derivative? You know, the significance of the significance of the ordinary derivative is nothing but the tangent, slope of the tangent, or lots of applications are there. But what is mean by or what is signified with respect to these partial derivatives? So here, since number of independent variable 2 and dependent variable 1, so we can actually accommodate all these three variables in a three-dimensional space. There is the xy coordinate, there is the z coordinate. So it represents a surface. So you know that if I consider a three-dimensional geometrical figure and try to draw a tangent, so your tangent won't exist. Rather here there will be tangent plane, because whenever I will be drawing the tangent, it will be the projection of this surface along xy plane. So there will be a tangent plane. So you know that whenever we are considering any vector in two-dimensional plane, we can actually divide this vector into components. One is parallel to x-axis and another is parallel to y-axis. So the resultant of these two vectors gives the value of original vector. Similarly, here also the tangent plane that we are getting, we can identify the tangent plane through a directional vector. So we can segregate this into components. One is parallel along x-axis, one is parallel along y-axis. So this component is denoted as del z del x, this component denoted as del z del y. So the tangent plane that we can draw on a surface, we can segregate this into components. One is along z axis, another is along x axis, parallel to x axis. So the component which we are getting, that is parallel to y axis, denoted as del z del y, that is a partial derivative of z with respect to y. Similarly, the component of tangent plane which you can draw along the parallel direction of x direction, that is denoted as del z del x. So these are the significances of partial derivative. Have you understood?
Yes, sir.
Have you understood or do you have any doubt?
Yes, sir.
Yes, sir.
Okay. Okay. Then we will move on to a function of complex variable. Okay, so let me find out. Similarly, here also, let us consider fz as a single valued function of z in the domain D. Then the derivative of the fz will exist at z0 if the limit of this quotient will exist. So here the independent variable is z and dependent variable is fz. So here independent change in independent variable is z, del z, and change in dependent variable is f z0 plus del z minus f of z0. So if the limiting value of this quotient exists, then we will say that the derivative will exist and derivative is denoted by f dash z0. So what is the significance of this derivative? So here you know that since z and w or z and fz both are complex numbers, so both must have real and imaginary part. So total there are 4 variables. So we can't identify all those 4 variables in a single frame of reference. So that's why you know that we need to consider two planes. One is the independent plane where we consider the independent variable z. Another is the dependent plane, that is the w plane, where we consider the dependent variable w. So what we are doing here, we are considering a point z0 where we need to find out the derivative. So if I consider any complex numbers in Argand plane, then it represents a two-dimensional point. So here z0 is identified by the point P. So if I consider any point P, then that can be joined by a Poissonal vector. So Poissonal vector means the vector that actually joins or that actually connects that point from origin, and the direction is towards that point from origin. So that is the P. So if I consider the increment with respect to this point, so along vector, then we are considering a vector that is perpendicular to that Poissonal vector. So that is small increment, so that is denoted as del z. So if I consider the vector law of addition, you know that if I consider a triangle, then along two consecutive sides, if we consider two vectors, then the third side represents the resultant vector. So since this is z0, this is del z. So ultimately the point Q will be identified as z0 plus del z. So Q is the point that is z0 plus del z that is joined by this Poissonal vector starting from origin. So you know that whenever we are defining this function fz, so each and every point which we are considering in the z-Argand plane, that means the independent plane, will be mapped to some points in the dependent plane, that is w plane. W plane, the independent, the real axis is u and imaginary axis is v. So p will be mapped to certain points in the w plane. So p is mapped to p prime. So p prime being the image of p has the coordinate, has a value of f of z0, that is denoted as w0. Similarly, q prime being a point in the z plane will also be mapped to q prime. So q prime, since is the image of q, so the value of q prime will be the point we can identify by q prime as the coordinate as f of z0 plus del z, that is w0 plus del w. So if we can join this p prime and q prime by a vector, so the value of this vector as per the triangular law of addition of vectors will be f of z0 plus del z minus f of z0. So p prime q prime represents the change in dependent variable and pq represents the change in independent variable. So p prime q prime divided by pq we will consider, and whenever p prime will come closer to q, then p prime will gradually coming closer towards q prime. So the limit of the cosine of p prime q prime by pq whenever p prime comes closer to q is defined or identified as a derivative. So if the limiting value of this cosine exists, then we will say that the function is differentiable, and geometrically this signifies uh, this is identified, or that is visualized by this. Is that clear till now?
Yes,
Okay. Is it clear to all of you? If you have any kind of
yes,
Yes,
doubts,
sir.
you could ask me. Yeah. Okay. Sure. And what are the properties of differentiability? So sorry, by mistake, I've written here continuous. It will be differentiable. So if two functions fz and gz are differentiable at a point z0, then their sum and subtraction of two functions will also be differentiable at that point, and the derivative of sum or subtraction of two functions is defined as this: d dz of fz plus minus gz will be the derivative of fz plus minus derivative of dz. Then the derivative of product of two functions will be the second function fixed, the derivative of first function, then first function fixed, derivative of second function. Then the derivative of cosine of two functions is denoted as this. So this is defined provided the denominator is not equals to 0. That means dz is not equals to 0. So then there comes a problem where we need to check the differentiability of the function fz equals to z bar. So here also, if we need to check the derivative, check the existence of derivative for a given function, then we need to use the definition. Definition means this is the definition. This definition we need to check. So if the limiting value exists for this quotient, then we will say that the function is differentiable at the given point. Otherwise, it is not differentiable. So here, no particular point is mentioned. So that's why we need to check the differentiability at any arbitrary point z. So f dash z is denoted by limit del z tends to 0 f of z plus del z minus fz by del z. So if the limiting value of this quotient exists, then it will exist, otherwise it doesn't exist. So here, since z is x plus iy, so the increment in z will also be dependent with respect to the increment of the real part as well as increment of imaginary part. So del z will be del x plus I del y. So whenever del z tends to 0, this will also tend to 0. Now f dash z is limit z tends to 0, del z tends to 0, f of z plus del z. So fz is z bar. So f of z plus del z is z plus del z bar minus f of z is actually z bar by del z. So z is x plus iy. So since del z tends to 0, so del z has a real part del x, imaginary part del y. So you can write it here as limit del x del y tends to 0 0. So z is x plus iy, so x plus iy plus del x plus I del y bar minus x plus iy bar. So that is limit del x del y tends to 0 0. X plus iy bar is x minus iy plus del x minus I del y minus of x minus iy by this. So x iy will be deducted here. So it will be ultimately converted to this one. Now, if the limiting value of this quotient exists, then we will say that the function is differentiable at any arbitrary point z. So you know how to check the existence of limit. So we need to show that the limiting value, if is indifferent with respect to any arbitrary path, then the limit exists. Otherwise, if the limiting value depends on the path, that means if I choose two different paths and limiting values are coming different, then at once we can say that the limit doesn't exist. So here we need to approach towards origin, that means the point 0 0. So if I want to approach towards the origin in a two-dimensional plane, then either we can approach through x direction or we can approach to y direction. So let us approach through x direction. So if we approach through x direction towards the origin, then y coordinate will also be 0, del y will be 0. So if you put it here, then this will be 0, this will be 0. So the limiting value will be dependent on x only. So that value will be 1. Now if we approach towards the origin through y direction, then del x will be 0. So then the limiting value will be dependent on y only. So this will be 0, this will be 0. So this will be minus I del y by I del y, limit of this. So that is minus 1. So while here we are approaching towards origin through x axis and y axis, we are getting two different values. That's why if I consider any two arbitrary paths, then obviously the limit doesn't exist. Limits are not equal, they are actually varying. So that's why here we can say that the limit of this quotient doesn't exist. That's why the function is not differentiable at any arbitrary point z where the function is fz equals to z bar. Is that clear?
Yes, sir.
Okay. Okay. So let us discuss one more example. Okay. So then there are two problems. I have already shared this in the Google Classroom. So you can try to solve the problem. If you can't solve it, in the next class you will be asking me, then I can solve this problem. Okay. Then let me share one screen. আরে একসাথে তুলে নিয়ে চলে এসো। Okay. Then we'll be discussing one more important concept here. Can I see the screen now?
Yes, sir.
Yes, sir. Yes, sir.
That is called analytic function. So just I am asking you one question, that if I consider a function of one real variable, say any arbitrary function fx, and I provide the set of real numbers, and I ask you to tell me whether this function is differentiable at any arbitrary real number or not, then how to proceed? Say any arbitrary function is given, say x cube sine x, y equals to say x sine 1 by x, y equals to the power x cos x. So lots of functions I can give. So if I give you an arbitrary function and I ask you to check whether this function is differentiable at any arbitrary point that is a real number, then how to check it? How you can proceed? Have you got my question? Have you got my question? Have you understood? Not. ওই তো আনবে
So can
বলছি।
you please repeat once?
So I am giving you arbitrary problem. Okay. I am giving you a arbitrary function. Let's say this function. So if I ask you to check whether it is differentiable at a particular point, let's say x equals to 3, then what you can do? You can use the first principle. You can verify whether this function is differentiable at x equals to 3 or not. Now, without giving a particular point, I am giving you an arbitrary point, which is a real number. That means in the entire real plane or real line, I can pick any arbitrary real number, and I am asking you to say whether this function is differentiable. This sort of function, any arbitrary function, is differentiable for any real number or not. Without giving a particular real number, I am asking to check the differentiability of the function in the entire set of real numbers. Have you got it now?
Yes, sir.
Then how to check? How you can proceed? Anyone? Whatever is coming to your mind, the answer may not right. Anyone? So if a arbitrary function is given, so without checking whether it is differentiable at any particular point or not, as a whole you won't be able to answer whether it is differentiable in the entire real line. So what you need to do, just you need to pick an arbitrary real number. Say for example fx equals to x square is given. So you need to verify the derivative of this function by using the definition for any arbitrary function f of x0 minus f of x minus f of x0 by x minus x0. So then you will be finding that this value is 2x0. Now if you take x0 as any real number, you will find that this will exist. Then so I can say that the function x square is differentiable for any arbitrary real number. So that means without checking the differentiability point wise, it is not possible for us to answer as a whole whether it is differentiable in the entire real set of real numbers or not. Is that clear? Is that
Yes,
clear
sir.
or not? Okay. So now we can actually do it easily if the function is function of complex variable. That concept is called as the analytic function. So this is only applicable for the function of complex variable. So this is not valid for function of real variables. Either it can be function of one real variable, function of two real variable. It is not possible. That means if a function is analytic, then without checking the derivative of a function pointwise as a whole, we can answer whether the function is differentiable for any arbitrary complex number or not very easily if the function is analytic function. So what is the concept of analytic function? So the concept of analytic function is that, let's say fz is a function of a complex variable z. If it is analytic at the point z0, that implies function is not only differentiable at the point z0, but around the point z0 we can consider or construct any arbitrary neighborhood, and if it is analytic, then function is differentiable at all these points which are enclosed within that neighborhood, within that arbitrary neighborhood. That means if I take any point, then I can consider any neighborhood, because neighborhood is not unique, I know, because I can change the radius, then I can consider different circular orbits. So if it is differentiable at the point z0, then it not only ensures that it is differentiable at that point, but it ensures that it is differentiable at all other points inside that neighborhood. Is that clear?
Yes, sir.
So
Yes, sir.
compared to this, if I consider the more broader concept, so this is the concept of analytic function is more broader concept compared to differentiability, because differentiability ensures only the differentiability at any particular point, but analyticity ensures that the function is not only differentiable at a particular point, but it is differentiable in the entire neighborhood that you could construct around a given point. Okay. Okay. So compared to this, if I consider analytic function in a domain. So all of you are familiar with the term domain. Domain means just we are considering any subset of the set of complex numbers. So this is a domains. So domain is any set in the Argand plane we can consider. So if analytic function in a domain means the function is not only different analytic at a particular point, but it is analytic at each and every point which is there inside the domain. That means it is analytic at that point, it is analytic at this point, it is analytic at this point, it is analytic at this point. That means since it is analytic at this point, so around this we can construct lots of neighborhood where the function is differentiable. Around this point I can construct different neighborhood where it is analytic. So analytic function in a domain means it is not only analytic at a particular point, but it is analytic at each and every point which is in the domain. So compared to this more broader concept, if we want to identify, that is called as the entire function. That means analytic function in the entire complex plane. So first we are considering only one point and we are saying that it is analytic at this point. Then we are considering a set in the complex plane and we are considering that the function is analytic in that domain. So lastly we are considering that it is analytic in the entire complex plane. That means any complex number if I pick, then the function will be differentiable as well as the analytic there. That means if I pick this point, around this point I can construct a neighborhood where the function is differentiable. If I consider this point, around that point I can construct a neighborhood where the function is differentiable. So at any complex number the function is analytic. So that is more broader compared to the previous one. Is that clear?
Yes, sir.
So that is told over here. So fz is said to be analytic at a point if fz is differentiable at every point in some neighborhood of that particular point. Then compared to that, analytic in a domain means it is not only analytic at a particular point, but around for each and every point which is there in the domain, I can construct a neighborhood and the function is analytic. So that means it is analytic in the entire domain. So analyticity in the entire domain is known as the holomorphic function, holomorphic in domain D. The third one is the function which is analytic in the entire complex plane is are said to be as entire functions. So that is more broader. So far we have studied the concept of differentiability for a function of one real variable or function of two real variable, which ensures the differentiability only at one point. But here we can consider this concept of analytic function for function of complex variable, where there are three cases. If I consider the analyticity at a given point, then it ensures that the function is differentiable in any neighborhood of that point. Analyticity in a domain means if I consider any point, then it is analytic at that point. That means around that point I can construct different neighborhood and the function is analytic. And then entire function means if I pick any point from the complex plane, then it will be analytic at that given point. So these three are concepts. Okay. So in the next class, I will be discussing how to check whether a given function is analytic or not. So if I know that the function is analytic, that is very much easier for us to check the differentiability in a given set, because we don't need to check the differentiability of that function at each and every point in the set. Rather, if it is analytic at that analytic at a given point, we can provide assurance that the function will be differentiable altogether in that set. So in the next class, I will be discussing how to check or what are the conditions through which we can check whether a given function is analytic or not. Okay. So just let me take your attendance manually first, then I'll be sharing the link. Rule number one. Rule number one, two,
Present, sir.
three,
Present, sir.
four,
Present, sir.
five,
Present, sir.
six,
Present, sir.
seven, eight,
Present, sir.
nine,
Yes, sir.
10, 11,
Yes,
11,
sir.
12,
Yes.
Present, sir.
13,
Yes, sir.
14,
Present, sir.
15,
Yes, sir.
16,
Present, sir.
17,
Sir, 17.
yeah,
17 present, sir.
18,
Present, sir.
19.
Present, sir.
So 19, you are attending my class for the first time. What happened to you?
Sir, medical issue, sir.
Sir, sir,
Yeah,
roll number
roll number
one.
1. Okay, so let me share the exam codes. So this is the exam code, and this is the link. Just click the link and provide your full enrollment number and exam code and complete the class test. So just tell me once whether you can access it right now or not.
Sir, it's working.
Okay, thank
We
you.
walk inside.
Thank you, Mosa. So complete the class test soon, and the class note of previous classes which I have shared in the Google Classroom, the problems which are given over there that I have not solved, just try to solve those problems, and if you face any problem, just in the next class let me know, I can solve. Okay, thank you all for attending today's class. So just finish your exam. So I am signing off. Thank you.